Hey everyone. So the next unit we're getting into is the study of acids and bases, which is topic 8. And this video is just going to take a quick introduction to in general, what acids and bases are. So acids and bases, probably something you've all heard of, at least in passing throughout your life. Even if you've done things like the classic volcano reaction with the baking soda and vinegar as an acid-base reaction. Okay, whether you know it or not, um, acids and bases are part of your everyday life, and you've experienced them and their reactions. So acids and bases, they are opposites, okay, and their reactions have been studied for literally hundreds of years, back to the ancient Greeks, Egyptians. Um, in those ancient civilizations, they didn't quantify them as we have today, but they did distinguish various acids and bases and their properties. Acid comes from the Latin word acidus, which means sour, and bases, which are also known as alkali. We'll get into the distinction a little later. So if they're soluble in water, they're alkali, and they come from the Arabic word alkali, meaning the ashes, and that's because of the feel. Things basically were called alkali if they had a slippery feel, which we now know is a property of a base. Okay, if I say his name right, Savante August Arrhenius. Okay, he was the first person, so he's credited as kind of the person to take acids and bases and bring our studies to the next level. So he was the first one to actually try to apply a definition to what an acid and a base is, and he was awarded the Nobel Prize for his work with acids and bases. So let's see what Arrhenius said about that. What was his definition? So he said that an acid is a substance that ionizes in water to produce hydrogen ions, or hydronium, which is H3O plus. So in the acid-base unit, we use the H plus for representing a proton or a hydrogen ion, and the H3O plus, the hydronium ion, we use those interchangeably. So for example, hydrochloric acid, when you react it or dissolve it into water, okay, it produces H3O plus and Cl minus, an ion. So when dissolved in water, it ionizes to produce protons. An Arrhenius base ionizes to produce hydroxide. So an example of that is ammonia. So ammonia, when dissolved in water, okay, produces NH4 plus and OH minus. So that H3O plus, that is what represents an Arrhenius acid, and this OH minus is what represents an Arrhenius base. So if something can dissolve to produce those. We'll look at some flaws in this definition later, but this was the original definition of what an acid and a base were. Okay, so what common uses do we have for acids? There's a lot, way too many to talk about here, but just some ones that you'll be familiar with. So acetic acid or ethanoic acid, for its IUPAC name, is vinegar. Okay, with the vinegar that you put on your fries or fish or whatever you want to put vinegar on. Citric acid, another type of acid, is what gives lemons, limes, and oranges. It's what gives them their sour taste. So that white powder that you find on sour, like gummy candies, that's actually just powdered citric acid. Ascorbic acid is vitamin C. So just another name for vitamin C, which we need to ingest every day to function. Sulfuric acid, as we saw back in the equilibrium unit, we talked briefly about this, is used in the production of fertilizers, steel, paints, plastics, among other things. And a lot of the times you've heard of battery acid. So acids are used in batteries to conduct electricity. Bases. Bases are so any soaps or ammonia. If you think of cleaning detergents, that most of them will have a base in them. So that's what actually gives soaps their useful properties. So that OH ions that we said get produced with when you dissolve a base. Those ions interact really strongly with dirt and grease and help wash them off. And we'll get into that later on as well and talk about things like surfactants in a later unit. Um, Chalk and oven cleaner are examples of familiar products that contain bases. Antacids like Tums or other. I personally use Tums, so I can't think of any other brands, but antacids that you take for heartburn are bases, and your blood is actually a basic solution. And contrary to popular diet beliefs, no, you cannot. The food you eat does not change the pH of your blood. Your blood needs to remain basic, and it does so. It's what we call a buffer solution, and it will keep it at a constant pH regardless of what you eat. So to sum up a couple of properties, so acids, when we talk acids and bases now, we have a pH scale. Okay, and our next part of this unit is all about the pH scale, but a pH of less than 7 is considered acid, and a pH of more than 7 is considered basic. pH of 7 is neutral. Okay, so acids taste sour, whereas bases taste bitter. So acids, think again of those sour candies. Bases is like soap. If you've ever tasted soap, it is quite bitter. Um, Bases feel slippery, so to the touch, but acids have no real characteristic texture. Litmus paper, if you take blue litmus paper, so you can see it in this picture over here, if you dip blue litmus paper into an acid, it will turn red. So this solution on the left would be an acid. If you take red litmus paper and dip it in a base, it will turn blue. So think base for blue when we're talking litmus paper or an alkali since it's dissolved in water. Phenolphthalein, which we've used before in some labs. Okay, phenolphthalein in an acid is colorless and in a base will be pink. Both conduct electricity when dissolved in water. And acids are corrosive to metals, whereas bases are non-reactive with metals, which is why when we're generally cleaning things like a stove cleaner or something like that where we're cleaning a metal object, we're going to be using a base because we don't want the metal to corrode, unless we're trying to get rid of rust, in which case we may use an acid. So we're going to look at just some common acids that you'll come across. Okay, so one is citric acid. Okay, this is an acid found in, again, lemons, oranges, things like that. You can see the part that's acidic on it, so I'll circle it here. Look at this. If you remember from organic chemistry, this is a carboxylic acid functional group, has the word acid in it, and we actually have 3 of them. So there's 3 sites on this carboxylic acids that make this group acid. When it dissolves in water, this proton can be released, okay, producing H plus on dissolving with water. Another example, this is actually the smallest carboxylic acid we have, methanoic acid, which we also call formic acid. This is what causes ant bites to sting. So they actually produce formic acid, and when they bite you, that gets injected in, and that's what causes the pain. Aspirin is a weak acid. Okay, and that's been used for over 100 years. Again, you can look, it's a weak acid. You can find that carboxylic acid functional group on it. That makes it acidic. Glycine. So this is an amino acid. Okay, so amino acids will actually have an amino group, which is an NH3 over here. Okay, or NH3, which actually makes them basic. So things when you see nitrogen in a compound, generally it's going to be basic, but it has that carboxylic acid group as well. So this piece, carboxylic acid, okay, which makes it acidic. So an amino acid actually has a basic portion and an acidic portion. Caffeine, okay, is a weak base. Look at all the nitrogen. So these nitrogens all are bound up with bonded to 3 carbons, but this one, right, would be our basic nitrogen on here. I guess all of them could technically accept a proton. We'll talk about proton accepting later in this unit. But caffeine, know that it has nitrogens, so it's a weak base. Lastly, sea slugs, okay, excrete sulfuric acid. So that's actually a defense. Now, for us humans, if we were around a sea slug as it was excreting it, it gets dissolved pretty quickly in the water since they do live in aquatic environments. Wouldn't be too dangerous to us, but to something trying to eat them or touch them or anything like that, it could cause some burns. Okay, so that is a brief introduction to acids and bases.